Hello everyone, welcome back to the course Introduction to Infrastructure Asset Management. This course is offered under MOOCs, an initiative of Government of India. Let us continue with our discussion on a multi-criteria decision making method known as AHP. In this method, till now we have seen that it includes 5 key steps. First, we start with problem decomposition. We saw that any multi-criteria decision making method can be divided into different tiers. We try to understand what is the goal, what are the different criteria under which the decision has to be taken, and what are the relevant alternatives. For example, in our case we saw that to select a right car there can be 4 different criteria: safety, reliability, economics and style. Then we saw that we can use a pairwise comparison matrix. By utilizing the Sati's fundamental scale, we can decide or assign priority to each criteria. We saw that we can compare safety in comparison to reliability and say how much safety is preferred over reliability. If they are equally preferred, we assign a value which is 1. If one of them is extremely preferred over another, then we assign a value of 9. So, we saw that we can get a pairwise comparison matrix like this, and we can do some numerical calculations on that to determine the average criteria weight. So, we saw that for each criteria we could assign or determine these weights. Then we saw that the next step was to compare each of our alternatives based on the given criteria. So, for example, safety, we compared car 1, 2, 3 and 4. Then we also compared these cars on the basis of reliability, economics and style. We created pairwise comparison matrix for each one of them. Then I had discussed how do we calculate weights. Then I had discussed how we calculate relative performance of each alternative on a given criteria. We had seen numerical calculations for safety. These were the numbers. I had requested all of you to do the same exercise for the remaining 3 criteria, that is reliability, economics and style. I hope all of you have tried this and you have the following results. The numbers for each of these should look something like this. If you see here, in case of reliability, the relative performance of each car is same, because when we discussed about pairwise comparison for reliability, we said that we believe all these cars are equally reliable. Thus, we had assigned an equal weight to all of them, and which can be seen here as well. The criteria weights for reliability for each of these cars, the relative weights for reliability for each of these cars are same, 0.25, 0.25, 0.25. Now, let us move on and discuss the next step, that is synthesizing the results. Once we have decomposed the problem, we have determined the weights for different criteria, and we have also understood what is the relative performance of each alternative on a given criteria. Now, the question is, how can we synthesize this information together to finally decide which alternative is the best? So, step 4 discusses synthesis of results. So, till now we have the relative performance of each alternative, and we also have the criteria weights. That is, here for each car, car 1, car 2, car 3 and car 4, we know what is the relative performance of each of these cars when it comes to safety, reliability, economy and style. These were the values. Also, we know that as a decision maker, we have given a weight of 0.60 to safety. That is, for us, safety is most important. On the other hand, we have given a weight of 0.06 to style, because we believe that when compared to safety, reliability and economics, style is not that important for us. I hope the idea is clear. We have not assigned these weights directly. We had used a pairwise comparison matrix to compare each of these criteria over another, and then using the Sartese scale and the concept of normalization, we had determined these weights. Now, the question is, once we have this information, how do we decide which car is the best for us? The way to do that is simple. We calculate overall relative weights. Overall relative weights for each alternative is calculated as follows. For example, for car 1, we say that the overall relative weight will be 0.11, that is the performance on safety, multiplied by the overall weight for the safety criteria, plus 0.25, that is the relative performance in terms of reliability, multiplied by the criteria weight for reliability. So on, 0.58 multiplied by 0.14 plus 0.05, which is the relative performance on style, multiplied by the overall weight for style, and we get the overall relative weight for car 1. Now, we can do this for all the other alternatives as well. Since these are relative overall weights, we cannot take a call just by looking at the performance of a given alternative. We must calculate the relative overall weights for all the other alternatives. Only then we can decide which alternative is best suited for us. So, before moving on, I encourage all of you to please pause the video and try to calculate the relative weights for car 2, car 3 and car 4. I hope you have done this exercise and you have determined that the overall relative weights for each of these cars are as follows. Here you see that based on the different criteria weights and the performance of different cars, we see that car 1 and car 2 have more or less equal relative weights. Similarly, car 3 and car 4 have similar overall relative weights. The alternative which has the highest overall relative weight is the one which should be preferred. So, the alternative which has the highest weight is selected by the decision maker. Now, let us dive deeper into these numbers. Here we see that car 1 and car 2 have similar overall weights. However, if you see their performances are different. For example, we saw that car 1 had a relative performance of 0.11 in terms of safety, and actually car 2 was more safe than car 1 because it had a relative weight of 0.17. However, when it came to economics, car 1 actually performed better than car 2. The way we had given weights, we feel that car 1 is more economical compared to car 2. Also, in terms of style, car 2 was better than car 1. Now, we had assigned different weights to each of these. Car 2 was better in terms of safety, and safety had one of the highest weights. On the other hand, car 1 was better than car 2 in terms of economics. Economy also had a weight of 0.14. Style didn't have a very high weight, and both these cars were equally reliable. Now, when calculating the overall relative weights, it so happened that both these cars got a equal score. Now, here one could say that both car 1 and car 2 are equally preferable to the decision maker. However, if they feel that safety is more important for them in comparison to economy, then they can actually go for car 2, because car 2 has a higher safety score. Or if they say economics is more preferred, then they could actually go for car 1. But please note that we are doing this only because both these cars have a same overall relative weight. Similarly, if we go to car 3 and car 4, we see that car 3 and car 4 are actually preferred options. They are preferred over 1 and 2. The main reason behind that is both these cars have a high safety score. Since safety had higher weights in our analysis, we see that the results favor these cars. Again, if you compare, one could say that car 4 is more preferred than car 3. Let us understand why that is the case. Here, we will see that car 3 and car 4 have same performance when it comes to safety and reliability. Now, when you come to economics, car 3 is better compared to car 4, and when it comes to style, car 4 is better. If you see the difference between these two values, when it comes to economy, car 3 and car 4 are more or less similar. Car 3 only has a slight edge, but when it comes to style, car 4 has more edge in comparison to car 3. Now, based on the relative weights, it so happened that car 4 comes out to be slightly more preferred than car 3. So, if the decision maker has to choose between these 4 cars, they should ideally go with car 4. They could create a case for car 3 saying that the overall relative weight is very much closer to car 4. So, we want to go for car 3. Once we have synthesized the results, the next and the final step is to check for consistency. The question which should come to your mind is, why do we need to check for consistency? Are there any reasons for inconsistencies in doing AHP analysis? So, let us discuss why do we need to check for consistency. The process of AHP was as follows. We had determined all the different criteria, and then we had done pair-wise judgments. Now, once these judgments are recorded, we need to check them for consistency. For example, on any given criteria, if you prefer car 1 to be twice as much more than car 2, please note this is on the Sati scale which we have been using, where 1 meant equally preferred, 2 meant slightly more preferred than another. So, here we are saying car 1 is slightly more preferred than car 2, but the number we have assigned is 2, and at the same time we are saying that car 2 is again twice as much preferred than car 3. The question could be, what should be your preference for car 1 with respect to car 3? So, I hope this particular concept is clear, that we are saying car 1 is twice more preferred than car 2. At the same time, we are saying that car 2 is twice more preferred than car 3. So, if someone asks us, based on this information, can you give us a relative importance of car 1 over car 3? Mathematically, the answer should be 2 multiplied by 2, that is 4, because we are saying that in comparison to 2, 1 is better by 2, in comparison to 3, 2 is better by 2. Now, if we use the transitivity rule, car 1 should have a preference of 4 over car 3. This is mathematically way of understanding this. So, the mathematically consistent answer is 4. However, if the decision maker has assigned a value such as say 3, 5 or 7, then there would be certain level of inconsistency. That is, when we ask the decision maker, how much would you prefer car 1 over car 3, and instead of saying 4, they say 3, it means there is some level of inconsistency. From a decision maker's point of view, it is difficult to keep all the results or all the comparisons consistent. Thus, we need to check for consistency, and also some level of inconsistency is expected in the analysis, and it is even allowed. I hope the concept of consistency is clear. Now, let us try to see this with our example of the car. We had said that we have 4 criteria: safety, reliability, economy and style, and we had created this pairwise comparison matrix. Now, let us check for mathematical consistency in the numbers which we have given for safety, reliability and economy. Here, let us remember that we were using Sati's foundational scale, where 1 meant both the cases are equally preferred and 9 meant one of the criteria is extremely preferred over another. Now, if you see, we said that for us safety over reliability has a rating of 3. We believe that safety when compared to reliability should have a value of 3. 3 is closer to 1, but it is greater than 1. So, it is more preferred than reliability. Similarly, we said that when we compare safety with economy, again we had given a score of 7. That is, in comparison to economy, safety had a very high preference. Now, based on this information, one could actually calculate what should be the relative preference of economy over reliability. Since we already have these numbers, we could say that based on the way we have defined the relative performance of safety and reliability as well as safety and economics, one could say that economics when compared to reliability should have a score which is around 7 divided by 3, which is 2 point something. Now, when we actually compare that, that is economy over reliability, we have assigned a value which is 1. That is, we said that we equally prefer these two things. This shows that there is some mathematical inconsistency. Ideally, we should have given a number of around 2 here. The question here is, how much of such inconsistency is allowed? For a decision maker who is trying to assess different alternatives and different criteria, it is very difficult to stay mathematically consistent all the time. Thus, we are trying to understand how much of such inconsistencies are allowed. In addition to the pairwise comparison metrics for criteria, there are other pairwise comparison metrics as well. For example, we had compared different cars in terms of their performance on the safety criteria. Again, we had some relative numbers assigned. Can you please check for the mathematical consistency in the way we have assigned performance of car 1, car 2 and car 3 in terms of safety? Again, in case of economics, we had a similar table. Again, try to check it. You would observe that there are some mathematical inconsistencies in the way we have assigned are pairwise comparison numbers. Thus, we need to check for overall consistency of our matrix to ensure that whatever analysis we have done is fairly consistent. So, we need to estimate how much of inconsistency is acceptable. Let us discuss how do we do that. Here, we try to calculate something known as consistency ratio or CR, which is given as the consistency index of the matrix under consideration divided by the consistency index of a random like matrix. Consistency index of the matrix under consideration is given by Ci equals lambda minus n divided by n minus 1, where lambda is the principal eigenvalue of the matrix and n is the number of criteria. In our case, n is equals to 4. I will discuss how to determine the principal eigenvalue of a given matrix. Now, we try to compare the consistency index of the matrix in comparison to the consistency index of a random like matrix. The idea of a random like matrix is that for these 4 criteria, we have just created a random matrix. We have not asked any decision maker for their preferences. We have just created a random matrix with random numbers. Obviously, for any random matrix, we should expect that the judgments will be highly inconsistent. So, overall, we are trying to compare what is the consistency index of the matrix which our users have developed or decision makers have developed. We are comparing it with a randomly generated matrix. I hope the idea is clear. Basically, the random like matrix Ri is the average Ci scores of 500 randomly filled matrix. In this paper, which was published in 2012, Ri values for matrices of different sizes is available. One can directly use that information. It is important to note that Ri value changes based on the size of the matrix. That is, if we have 3 criteria, then Ri will be different. If we have 4 criteria, we will see a different value. And similarly, if we have 5 or 6 criteria, the value of Ri will be different. Moreover, this work by Sati in 2012 recommends that for the scale which we have considered, that is the 1 to 9 scale, a consistency ratio of 0.10 or less is acceptable. That is, as long as we have a consistency ratio of 0.10 or less, we say that it is acceptable. However, if the value is greater than 0.10, then we should actually revise our judgments. We should locate inconsistencies in the matrix and we should check with the decision makers and request them to revise their estimates. So, the question is, how do we calculate CR? We have already seen that CR is given as the consistency index of the matrix under consideration divided by Ri, where Ci actually given by lambda minus n divided by n minus 1. N is straightforward. Let us discuss how do we determine lambda, that is the principal eigenvalue. I will just discuss one way to do this. To calculate lambda, we actually calculate the dot product of the pairwise comparison matrix and the priority vector. Basically, we are trying to do a weighted sum here. Then we basically divide these weighted sums by the corresponding priority vector to determine different lambda values. So, in the first step, we know that we have 2 such matrices available with us. The first one is the pairwise comparison matrix and we had used this information to calculate the priority vector or the different weights. Now, we try to calculate dot product of these two matrices. I hope all of you remember what is a dot product from your high school days. So, these two matrices can be written like this, and we have to calculate dot product for these. Please try to do it on your own. The way we do this is, we multiply the corresponding row with the column matrix given here. So, 1 multiplied by 0.6 plus 3 multiplied by 0.20 plus 7 multiplied by 0.14 plus 7 multiplied by 0.06 will come in the first cell here, and similarly you can do it for all the other rows. Please try to do it on your own, and you should get a matrix like this. So, this is the weighted sum matrix. Now, as discussed, the next step is to divide these weighted sums by the corresponding priority vector. So, we basically write all the weighted sum here and divide them by the priority vector under consideration. Here we are just dividing corresponding values. So, 2.60 divided by 0.60 will give us lambda 1. 2.60 divided by 0.60, lambda 1 is 4.33. Similarly, you can do this for all the other cells as well. Finally, you will know that the corresponding lambda values are as follows. Once we have done this, the next step is we use all these values of lambda and sum them, and then we divide them by 4 to find the overall lambda. So, in our case, the lambda is 4.16. Now, to calculate Ci, we know that Ci is equals to lambda minus n divided by n minus 1. The lambda is 4.16, which comes here, minus n is the number of criteria, which is 4, divided by 4 minus 1. So, the consistency ratio is given as Ci divided by Ci of a random like matrix, that is Ri. You would see that for n is equals to 4, Ri is equals to 0.9. So, we calculate consistency ratio Cr as 0.05 divided by 0.9, which is 0.058. Since this value is less than 0.1, we say that this matrix is acceptable for our AHP analysis. Now, after this, I encourage all of you to check consistency ratios of all the other pairwise comparison metrics which we have discussed in this example for selecting the right car. Try to solve it on your own. We will upload solutions for these separately. With that, we end our discussion on a multi-criteria decision making method known as AHP. We saw that AHP is a systematic approach for breaking down complex decision problems into manageable hierarchical components. It is a widely adopted method in multi-criteria decision analysis. Once we do AHP, it is important to check for consistency in the analysis. In this particular lectures, for calculating overall priorities and weights, I have used a method which is more approximate in nature. We have used the concept of normalization. This is an approximate method which is only suitable if the overall consistency ratio of the matrices is within the acceptable limits. However, alternatively, there is an exact method to calculate overall priorities. We do this by raising different matrices to different powers. until we get identical values. However, for our discussion, that is beyond the scope, and we will just restrict ourselves to the method which we have discussed in this particular lecture, where to determine priorities and weights we are using normalization. With that, students are encouraged to go over these references if you want to learn about this particular topic. I want to end this lecture here. Thank you. Thanks for listening.